Welcome back, students. Today we are going to look into symmetry a little bit more and discuss how we can represent symmetry mathematically using the character tables as a representation for the symmetry of molecules and some aspects of group theory. The learning goals from today are going to be able to extract symmetry information from the character tables that represents the symmetry of various groups of molecules. And then we're going to want to be able to assign basis sets to the character tables. And so this is going to take the place of things like orbitals. We're going to be able to look at certain orbitals and also rotations in certain dimensions and assign them to different representations here of our symmetry. And then we're going to use it to build up molecular orbitals. At the end of the last lecture, we ended on this multiplication table that told us what happens when we do successive symmetry operations to our C2V point group. We got this information using the matrices we developed. We had those 3x3 matrices. So if we do one twofold rotation followed by a second twofold rotation, we end up at the symmetry of the identity operator. We haven't changed the molecule at all. Now, it's pretty surprising, but we can also represent this information in the following character table down here. And it's not at all obvious how this information, these ones and minus ones, reflects this information here. But it turns out that they do. This character table reflects the same information that the multiplication table does, even though we only have one number. Now, how does it do that? Well, let's consider the following operation. We want to take a one mirror plane followed by a twofold rotation. So if we go to our character table, if our first operation is this mirror plane and the second is this C2 rotation, we should end up at the other mirror plane, the sigma v prime. So what happens if we do the same thing with these weird numbers? Well, the C2 numbers here are 1, 1, minus 1, minus 1. We can see that here in this table. And the sigma v numbers are 1, minus 1, 1, minus 1. Again, we can see that in the table. So if we multiply these by each other, we get 1 times 1 equals 1, 1 times minus 1 equals minus 1, minus 1 times 1 equals minus 1, and minus 1 times minus 1 equals 1. So our new vector here upon multiplying these together is 1 minus 1 minus 1, 1. And we go ahead and see that that is represented here in the sigma v prime slot on the table. So all of this information, we could do this for any other of these combinations and we would get the answer that we expect. So let's go through this character table and see what we can do with it. So the first column are the labels of this character table. So we have A1, A2, B1, and B2. Do these labels look familiar to you? And hopefully they do, because they should. We've seen them before when talking about symmetry adapted MOs. So the molecular orbitals for things like water and formaldehyde that we talked about a couple of lectures ago, it turns out water and formaldehyde are members of the C2V point group. So the molecular orbitals share these names of the representations of the C2V point group. And we'll see why that is at the end of today's lecture. The origins for this here, the A is something that is symmetric around the principal rotation axis of the molecule, and the B is anti-symmetric. So that's where the A and the B labels come from. The 1 and the 2 labels come from being symmetric or anti-symmetric around an axis perpendicular to the principal axis. So we have these different labels based on different types of symmetry. Now, what do we do with the next column? So this next column here is E, and E is the identity operator. So the fact that this column is entirely 1, that means that when we do the identity operator on any of these representations, A1, A2, B1, or B2, we don't change the sign. And that makes sense because we are literally doing nothing to the molecular orbital or anything of this symmetry representation. C2, on the other hand, will not change the sign of anything in the A1 or A2 representations, but it will change the sign of the B1 and B2 representations. So I want to skip ahead a little bit here and show us that this is the case. Okay. So looking at some of these orbitals, let's go ahead and evaluate the statement that I just made. So this is an A1 molecular orbital for water. And if we do a twofold rotation, so if we rotate this around the axis going through the middle of the molecule, we don't change the sign of anything. And the same is true for an A2. We don't have an A2 here, but we can look at those in class. Now, we said that the B1 and B2 representations should change sign. Here we have B2 representations, and we can see that these would, in fact, change sign upon a twofold rotation around this principal rotation axis. So we can go through and assign this to various groups. Now, in this kind of picture, we only have A1s and B2s, but if you look at A2 representations and B1 representations, we'll do this in class, and we'll see that they follow this character table here. So this shows us that all of the information we need is described in this character table. Okay, so we can do the same thing for the two mirror planes here as well. The next thing we want to be able to do is, like I said in the learning goals, is can we figure out representations of these point groups? And so we'll do that by considering what happens first to X, Y, and Z axes. So we have this picture of water here because it's part of the C2V point group. And when we're talking about the X, Y, and Z axes, we got to make sure we know what our coordinate system are. And this was, it doesn't really matter, but now it's been set to be this way. So we kind of have to use this notation. There's nothing special about the Z or X or Y axis. They're just chosen to be in the way that they are. So starting with X, what happens to the X axis upon these rotations? Well, for the identity operator, the X axis remains unchanged. For the C2 operator, it becomes negative of what it was. For the sigma V operator, it remains unchanged. And for the sigma V prime, it becomes negative of what it was. So what does that mean? It means we can represent the symmetry operations of the X dimension with 1, minus 1, 1, minus 1. And if we come down here and look, that puts the X-axis as a member of the B1 representation, where it has 1, minus 1, 1, minus 1. And we can do the same thing for Y and Z. So Y should be 1, minus 1, minus 1, 1. And that puts Y as a member of the B2 representation. And then Z is 1, 1, 1, 1. So Z is a member of the A1 representation. And it's pretty easy to see from these kind of tables that this is how it goes. We can also do this for rotations. And so what we'll do for rotations is look at the X-axis here. And we'll say, well, what happens if we did a rotation along this X-axis? So if we picture rotations in the X-axis, that would be the X-axis is coming through the molecule here. So rotations in the X-axis would be bringing these hydrogen atoms up and around and swinging the molecule around this way. And if we think about what happens to this, so if we leave it unchanged, the identity operator gives us a sign of 1. If we do a C2 rotation along this axis, that's going to change the sign of our rotating molecule as it rotates in the X-axis. So we have a minus 1. If we reflect across this mirror plane that's perpendicular, we're also going to get a minus 1. But if we reflect across the mirror plane that is in the same plane as the rotation, we would get a sign of 1. So a rotation in the X dimension is the same as our B2 representation. And we're not going to think too much about rotations. They're going to come in handy for figuring out the representation of the vibrational modes. But all we need to do is look at this information here. We can do similar things with other orbitals. We don't just have to have our X, Y, and Z dimensions, which also go to the X, Y, and Z orbitals. But we can do the same thing for, say, the D orbitals. So we can look at these and say, well, what happens for X and Y? And to figure that out, we just have to take the product. So here in the E operator, X is 1 and Y is 1. So this should get a sign of 1. Here we have X is minus 1 and Y is minus 1. Multiply those together, we get a sign of 1. Here X is 1, Y is minus 1. So we have minus 1, and then minus 1 times 1 is minus 1. So an XY is a representation for the A2, a member of the A2 representation. And we can see, looking at the p orbitals, that this works pretty well. So our p orbitals that lie on the X, Y, and Z axes fit in with the x, y, and z axes in terms of their representation. So the p orbital is, the px orbital is a member of the b1 representation, the py orbital is a member of the b2, and the pz orbital is a member of the a1 representation. And in the same way, a dxy orbital would be a member of the a2 representation, the dz squared, the a1, and so forth. So these character tables help us identify the symmetry of the orbitals. And in the most cases, you're just going to grab these character tables and look up this information. So you can grab this and say, oh, my central atom, my molecule belongs to the C2v point group. That means the z orbital is a member of the A1 representation, and so forth. I want to mention here the dimension of a representation. And this is something that's mostly just so you guys are aware of it, and we're not going to work too much with multidimensional representation. But our C2v point group we were able to distill that down to just a single number. It contains only one-dimensional representations. And that's because the x dimension only transforms based on the x dimension, not a sum of x and y or x, y, and z. So when we had our matrices that talked about how we transform from one coordinate system to another upon our symmetry operations, they were all diagonal matrices. We just had A, B, and C. It's also possible that you can't do this for more complex symmetry type, and you might need 2 or 3 dimensional irreducible representations. We can figure this out by looking at the matrices if we have them. And there's also a thing from group theory that tells us that the dimensions of the representation is related to the order of the group. So what are these numbers here? Well, H is the total number of symmetry operations that there are. So H is the order of the group. And then the D, so the J here is the number of different kinds of representations, and the D is the order of those representations. So or for our C2v point group, we have 4 different kinds of representations. We have E, the identity operator, we have a C2 rotation, and then we had a sigma V and a sigma V prime mirror plane that were not interconvertible. So we had 4 different representations, and they need to add up to the order. The squares of those need to add up to the order of the group, which is 4. So they all have to be 1, and they're all one-dimensional representations. Another example for that is not true is the C3v point group. That's something like ammonia has. So we looked at this before last time, but the C3v point group has 6 symmetry operations. And so that means it has an order of 6. And so those symmetry operations are a 3 mirror plane. So we have 1 mirror plane, 2 mirror planes, 3 mirror planes down every NH bond. Then we have the identity operator for 4, and then we have a forward rotation and a reverse rotation. So there's 6 different things we can do to this molecule that leave it unchanged. However, these belong only to 3 classes. So they belong to 3 classes because if I keep doing these rotations, I end up at the same thing. So 2 of the C3 rotations is the same as the C3 minus 1 rotation. And so that means these rotations are in the same class. And in the same vein, if I do a rotation, my sigma V1 mirror plane here becomes my sigma V2 mirror plane, and then it becomes my sigma V3 mirror plane. So those mirror planes are all in the same class as well. So what that means is that I have only 3 classes that I can have, so 3 different kinds of representations, and the squares of all these numbers have to add up to 6. And the only way to do that is if one of these is a 2-dimensional representation. And we can look at this if we think about how these rotations work. Since I'm doing a 3-fold rotation, I can describe my rotations as follows. So the rotational matrix here is cosine theta minus sine theta, cosine theta, and then the z is unchanged in this case. This is also true for the C2v point group, but I was doing a 180-fold rotation so that these became -1 and -1 at 180 degrees, and these became 0. For ammonia, if I'm doing a 120-degree rotation, these are not all 1s or 0s. And so we get a complex representation. And what this means is that my coordinate that's based off of x here, if I move it over here, is now based off of x and y. So the transformations are not just simply dependent on 1 dimension, and therefore it is a 2-dimensional representation. We can talk about these matrices by simplifying them down to 2 dimensions. We can't do 1 dimension because we don't. We have this 2-dimensional irreducibility here, and we can go ahead and see these symmetry operations here. What the matrices actually do to accomplish these transformations. And I'm not going to go into this in too much detail. Again, our focus is going to be on the math, which is much easier to do, although more or less the same with these more complicated ones, but it's easier to do with simpler point groups. So our focus is going to be mostly on 1-dimensional representations. But we can represent these mathematically as well and use this to come up with a character table that we'll see in the next slide. So we have the C3V character table here. And what we'll do is figure out what these representations are. So everything has to have an A1 representation that represents doing nothing to the molecule, more or less. And so we have this A1 representation that has all of these ones here. To figure out what the representation for these other ones are, we have to sum the diagonal elements of the matrices. So the multi-dimensional representation gets the sum of all of the elements in its diagonal column there, and that gives us the numbers here. So if we go back to this slide, if we sum the E here, we get 2. If we sum the sigmas, we get 0. And if we sum the rotations, we get -1. So coming back here, we have a 2, -1, 0. Those are the numbers that go into this character table. And that's what this information in the character table means. And we usually give the label to these multidimensional matrices or character tables as E. So that's what this E number or label means when we see it. Now we can ask what the third element is, and I'm going to go through this pretty briefly here. The third element, we can use group theory to predict what it is. And the idea from group theory is that the dot product of 2 representations from the same group is equal to 0, unless they are the same representation, in which case it equals H, which is the order. So we can see that if we were to do this, if we were to take the dot product of A1, we get 1 times 1 is 1, and then we have 1 times 1, but then we also have to multiply by 2 for the 2 rotations, so 1 plus 2, and then 1 times 1 times 3 is 3, so 1 plus 2 plus 3 equals H, the order of the group. So that's how we use this idea from group theory. Now, what can we say about this then? Well, we use this other part where if we take the dot product of these 2 different guys, it must be 0. So we can go ahead and do that using the same kind of idea that we did before. So the dot product between our unknown dimension or unknown representation and A1 gives us A times 1 plus B times 1 times 2 plus C times 1 times 3, and that must equal 0. So A plus B plus C has to equal 0. We do the same thing for our other representation. We get 2 times A times 1 minus 1 times B times 2 and 0 times C times 3 for 2A minus 2B equals 0. So this tells us that A equals B, and we can use that to solve for what this is, and C equals minus A, which is -1. So our representation here for our second group is 1, 1, -1, which gives it an A2 representation. And you can look up these character tables in the back of the book, and they're going to tell you the kind of information that you need to know here. So we can look and say, well, in this case, the PZ orbital is a representation, or is a member of the A1 representation. And then we have other things like x squared plus y squared, x squared minus y squared, and so forth that are different members of these other representations as well. The last thing that we want to do here today is to use this kind of information to actually make molecular orbitals. So the main thing that we've been doing here, thinking about symmetry, is we have unchanged molecules that are affected or unchanged upon these symmetry operations. So we do a rotation, we end up with the molecule looking the exact same, so it's unchanged. And what that means is that the total energy is also unchanged. And then what that means is that these symmetry adapted molecular orbitals, which give us the total energy, are unaffected by the symmetry operations. So that means that they are eigenfunctions of the symmetry operators because they're unchanged upon they're multiplied by ones and minus ones and so forth. And their energy is also unchanged. So they are eigenfunctions of both the total energy operator and the symmetry operators. And this is why we have these, or we focus on these symmetry adapted molecular orbitals from molecular orbital theory, because the valence bond orbitals, the hybrid orbitals, don't do this. So they're not operators of the symmetry operators. They're not eigenfunctions of the symmetry operators. That means that we can use symmetry in group theory to predict which atomic orbitals will participate in forming molecular orbitals. So we'll go in and look at the kind of ideas from group theory that tell us this. So the first question I'll ask is, what atomic orbitals are available to bond in water? And the answer is, of course, we have the two orbitals from the hydrogen atoms. We have a 1s atom from hydrogen A, or a 1s orbital from hydrogen B. And we have the 2s, 2px, 2py, and 2pz orbitals from the oxygen atom. And then the next question we want to address is, what's the condition for bonding? And it's the same condition that we've had before, that we need net overlap between the atomic orbitals. And before we said, well, they have to have the same type of symmetry. And that idea comes from group theory. So the overlap integral is the same as we had before. It's this Sij number that needs to equal the product of one of our wave functions times the other one. And if this is non-zero, we have net overlap. So we want to figure out when this will be non-zero. And what we're going to do for this is we are going to set up combinations of the hydrogen atom orbitals. So we're going to set one combination where we have a phi plus, which is when we add the hydrogen atom orbitals together, so they're a symmetric addition. And then we're going to have an anti-symmetric one where we subtract them from each other. And we want to say, well, what types of orbitals from the oxygen atom are capable of interacting with this? And what we need to do is figure out then what this is. So this overlap integral, this Sij, is simply a number. And so then we can ask the question, how does a number change upon doing symmetry operations? And what we'll find is that, well, it doesn't matter what kind of rotations or reflections or anything I do to the number 2, it's always just 2. It doesn't depend on x, y, or z, so manipulating it in regards to x, y, and z doesn't change it. So that means it doesn't change at all upon symmetry operations, and it must belong to the A1 representation. And so from group theory, we can find that if we take the product of any two things that belong to a group, they equal something else, and they only are going to equal something in the A1 representation if they are in fact the same representation. So what that means is that in order to have an oxygen orbital interact with the phi plus here, or the phi minus here, it has to belong to the same representation as the phi plus or the phi minus. So like I was just saying, the character of the product of any two representations is given by the product of those representations. So if we have our A2 and our B2, and we say what happens when we put these two things together, we just multiply out these matrices. So you've seen this before. So we have 1 times 1 is 1, 1 times minus 1 is minus 1, minus 1 times minus 1 is 1, minus 1 times 1 is minus 1. And so if we multiply A2 by B2, we end up with a B1 representation. And if we do two of the same, so if we do A2 times A2, we get A1. And this is something that's a general, something that we can show from group theory. So we have to have two characters that are the same in order to get the A1 representation. And remember, we're trying to get a constant, that overlap integral, which belongs to the A1 representation. So that means that the only things that could possibly overlap with our hydrogen atom orbitals have to belong to the same representation as them. So what representation do they belong to? We can look at these and say, well, what happens upon all of these symmetry operations? So for these guys, if we do nothing, we get 1, we're not changing the sign. If we rotate around this axis, we also don't change the sign. If we reflect in this way, we don't change the sign. If we reflect in this way, we don't change the sign. So our sigma plus here belongs to the A1 representation. So that means that only atomic orbitals from oxygen that also belong to the A1 representation will be able to participate in bonding with those guys. And here in the anti-symmetric combination, we can see, again, if we do nothing, if the identity operator gets us 1, a rotation gets us -1, a reflection in the mirror plane gets us -1 in this mirror plane, and in this mirror plane, we get 1. So that means it belongs to the B2 representation. So in this setup, we have our phi plus belonging to A1 and phi minus belonging to B2. And so what that means is that phi plus can only form molecular orbitals with S and PZ. Here we see Z, and then the S comes from being x squared plus y squared plus z squared. So S is also a member of the A1 representation. And the minus here can only form with PY, that also belongs to the B2 representation. And PX is non-bonding. And we can go ahead and look at all of the MOs. Again, we've seen them. These are the ones that are occupied for water. And we can see the characters here that we label them. We have A1, a 1A1, 2A1, 3A1. And the 1, 2, 3 just comes from strictly being the lowest, the next highest, and so forth. And they all have A1 symmetry. And then these orbitals have B2 symmetry. So you should go back and take a look over the orbitals for formaldehyde and check that they correspond to these types of symmetry. I'll finish off there for today. What we're going to do next time is attempt to apply group theory to determine the symmetry of vibrational modes. And so we'll see how we do that. And this is going to tell us what vibrational modes for molecules are active. Again, focusing on things like the C2B point group.